In question 22 we have this titration question. So we've got all this information, and then it gives us a results table for the volumes of HCl added from the burette, and the first thing it asks us to do is to complete the table. So remember, the titer is just the subtraction of the final volume, take away the initial volume, so it's just that minus that each time for these. Where you have to be careful is if you do that on your calculator will tell you that the answer is 24.2. But you have to remember that because these data are given to 2 decimal places, the second one always being 0 or 5, you have to give your titer to 2 decimal places, the second one always being 0 or 5. So that's not just 24.2, it's 24.20. If you don't do that, you don't get the mark. So the same for this one. If you do that subtraction, you get 23.85. And if you do this one, you get 24. Again, not just 24.3, but 24.30. So that's your completed table. And then in the second part, it asks you to find the suitable mean. Now it tells you that none of these is a rough one. The rough one was omitted. If there had been a rough one, you wouldn't have included it in the mean, but that's not an issue here. So all of these are eligible. And what you do is you look for the ones that are most closely clustered. And you can see in this case it's very clear that that's this one and this one. Okay, because these are only 0.1 apart. This one is a lot further away. Okay, it's closest to that one, but it's 0.35 away. So that's a much bigger separation. Even if it had only been a slightly bigger separation, you just apply the same rule, that you just take the ones that are most closely clustered. So that will therefore mean that those are the appropriate ones. So the mean is 24.20 plus 24.30 divided by 2, which is 24.25 cm cubed is your answer. So now in part B we've got to use these numbers to calculate the concentration of the HCl. So remember, these titration calculations always have the same general layout, at least at the beginning. And so you know that you start by working out the moles of one of the substances because you know both the concentration and the volume of that substance. So in this case, it's the sodium carbonate, where we know the concentration is 0.15 moles per dm cubed, and we know the volume that we used in the titration was that. And so we have to just do the usual thing and say that the moles of Na2CO3 is concentration times volume in dm cubed, which is 0.150 times 25 cm cubed divided by 1000 is 0.0250 dm cubed, which equals 3.75 times 10 to the minus 3 moles, or 0.00375 if you like. So then you say, okay, that's the moles of sodium carbonate, we're interested in the HCl, and what relates those is the equation. And in particular, this is where this number 2 comes in, because that tells you that the moles of HCl is twice as many as the moles of sodium carbonate. So you write that down. Mole of HCl is 2 times the moles of sodium carbonate from the titration. So we just double that number and we get 7.50 times 10 to the minus 3 moles. Okay, so now we know the moles of HCl, but it wants the concentration. So that's actually easy, because we just get that concentration is equal to moles over volume in dm cubed. We've got to make sure we get the right volume here. So what we've calculated here is the moles of HCl in the titration. So we want the volume in the titration. So it's 7.50 times 10 to the minus 3 divided by the volume in the titration, which was 24.25 cm cubed. So that's 0.02425. which works out as 0.3092785 on your calculator, but it tells you must give your answer to 3 significant figures. So remember, the first significant figure is that 3, so it's going to cut off here, and because that number is less than 5, it's going to round down to 0.309. Okay, so that's equal to 0.309. It's a concentration, so the units are moles per dm cubed, to 3 significant figures is the answer. So part C then brings in the idea of percentage error on these 2 volume readings that were involved in the, or 2 types of volume readings that were involved in the titration. So it gives you the uncertainty on each pipette volume and on each burette reading. Now with a pipette, remember, to get that volume of 25 cm cubed, you only effectively make 1 reading, because your pipette, remember, looks kind of like this. And the idea is that it has this single graduation mark on there, and you just fill it up so that the water, or rather the solution level, is just sitting on that line. So there's only 1 reading involved, which is making sure you've got the volume in the right place. So that means for the pipette, we can easily calculate the percentage error. Is equal to the uncertainty, or the maximum uncertainty, divided by the volume measured, or the quantity measured, which in this case is a volume, times 100. That's the definition that you need to know. So that's going to be equal to 0.04. Don't worry about the plus or minus, because that means that the furthest away you can be is 0.04. So that's what the uncertainty is. It's just emphasizing that it could be either below or above, but it's just 0.04 is the uncertainty, divided by the quantity measured, which is 25.0 cm cubed, times 100. And if you work that out, that comes to 0.16% on the pipette. Now with the burette, that's this kind of piece of equipment with the tap at the bottom. What you have to remember is that to get a burette volume, the titer requires 2 readings, the initial one and the final one, and each one of those readings will have an uncertainty of 0.05 cm cubed. So in other words, it might be filled up to here initially, and you would read off a volume there. Okay, so you get your initial reading, and that has an uncertainty of 0.05, and then you run some out and you get a final reading which is there, and that also has an uncertainty of 0.05, and they could be in opposite directions. So this one you could be overestimating and this one you could be underestimating, or vice versa. So the maximum total uncertainty is actually 2 times 0.05 cm cubed. So therefore the percentage error is 2 times 0.05 divided by the volume measured. You could use any of the 3 individual ones, or you could use the mean. So if we use, say, 24.20 as an example, and multiply that times 100, you get 0.41% as the error. But as I say, you could get slightly different numbers if you used any of the individual titrations, or you could use the mean one and get that number. So the important difference is recognizing that where your number you work with relies on 2 separate readings, you have to add together the errors on the individual readings. So just to make sure you've answered the question, it said which one has the bigger percentage error, and obviously that number is bigger than the 0.16% that you got for the pipette, so the burette has the bigger uncertainty.